Good morning, students. Today we will focus specifically on the kinetics of microbial destruction, the mathematical foundation behind thermal processing. Understanding kinetics allows us to design safe pasteurization and sterilization processes based on scientific calculation, not guesswork. Let us begin with the meaning of microbial destruction kinetics. We start with an initial microbial population. Heat is applied. Over time, the population reduces. Kinetics studies three main aspects: microbial death rate, population versus time relationship, and temperature dependence. In simple terms, it explains how fast microorganisms die under a given temperature. Next, observe the reaction rate in microbial inactivation. At time t equals 0, population is maximum. After a small time interval, a constant fraction dies. After another interval, again the same fraction dies. This indicates first-order reaction behavior. The rate constant K, expressed per minute, represents death rate. Higher temperature increases K, which means faster inactivation. The log reduction concept simplifies microbial calculations. 0 log means no reduction. 1 log reduction means 90% killed. 2 log reduction means 99% killed. 3 log means 99.9% destruction. Log reduction is calculated as LR equals log 10 of N0 upon N. This method allows us to quantify lethality precisely. Now, let us connect decimal reduction with temperature. The D value represents time required at a specific temperature for 1 log reduction. Graphically, D value decreases as temperature increases. This is shown in the D value versus temperature graph. The Z value is defined as the temperature increase required to reduce the D value by 90%. Thus, D relates to time, Z relates to temperature sensitivity. Here we see the mathematical expression of first-order kinetics. The exponential form is n equals n0 multiplied by e to the power minus kt. This shows population decreases exponentially. The logarithmic form is log 10n equals log 10 n0 minus t by d. This linear form is used for practical calculations. The relationship between K and D is K equals 2.303 by D. Therefore, knowing D value directly helps calculate reaction rate constant. Let us examine the graphical representation of destruction rate. When log n is plotted against time, we obtain a straight line. This is called the survivor curve. The linear region confirms first-order kinetics. The slope of the line indicates death rate. Steeper slope means faster destruction. The slope of the survivor curve has direct mathematical meaning. Slope equals minus 1 by d. If slope is minus 0.5, then minus 0.5 equals minus 1 by d. Therefore, d equals 2 minutes. This simple relationship allows us to determine D value from experimental graphs. Let us connect kinetics with milk processing. The process follows: raw milk to heat to hold to cool. The time temperature profile, such as HTST at 72 degrees Celsius for 15 seconds, ensures required lethality. Three key parameters govern the system: D value, time for 1 log reduction; Z value, temperature change for 10-fold D change; F value, total lethal effect of the process. These parameters guide industrial process design. This visual summary integrates all concepts. D value controls time, Z value controls temperature sensitivity, F value represents total lethality delivered. First-order kinetics model connects all equations. N equals n0 multiplied by e to the power minus kt. Log 10n equals log 10 n0 minus t by d. K equals 2.303 by d. Log reduction, log 10 of n0 upon n. All these are interconnected within the first-order kinetic framework. To conclude, microbial destruction during thermal processing follows predictable mathematical behavior. D, Z, and F values form the backbone of process validation. Proper understanding of kinetics ensures safety, regulatory compliance, and product quality retention. Mastering these principles is essential for dairy engineers and food safety professionals. Thank you.